Make a start. What I want to do is to look at how do you find a determinant of a 3 by 3 matrix and a 4 by 4 and an n by n matrix. Okay. Now this is a 3 by 3 matrix. All determinant of a 3 by 3 is given by determinant of A of that matrix is given by A times the cofactor of A plus B times the cofactor of B plus C times the cofactor of C. We missed you in the first hour, Tafiq. We knew you weren't there because no one answering questions apart from Patrick. So you shouldn't be skiving. So we shouldn't answer questions, otherwise we wouldn't know you weren't here. Okay, so this is the determinant of A. That's how you find the determinant of A. Okay, and what about if we expand that? What's the cofactor of A? How do you find the cofactor of A? What is that? Yep.
So E, F, H, I.
Yes, right. So it's going to be A. What's wrong with this pen? The other pen, isn't it? A, okay, times by the determinant. Yeah, sorry, you've got to put determinant of E, F, H, I. Yeah, you cover that up, okay? Determinant of E, F, H, I. Yeah, okay. And then, what about this second? Yep.
Minus B.
Yeah, minus, isn't it? Why is it minus now?
Because where the B is in the plus.
Yeah, of course, minus sign, or you can do it as 1 plus 2, isn't it? Yeah, minus 1 to the 1 plus 2, which is minus 1, isn't it? Minus 1 cubed. So this is going to be minus B, yeah? Determinant of what? Determinant of what? Come on.
DF.
Yeah, DF, yep. GI. Look, some of you who weren't here, I'm glad I read up some, or you either done it before. Plus C, is it plus C or minus C?
Plus.
Yes, plus C, determinant. Okay, determinant of what? The cofactor of C, which is what? D, E, G, R, H, isn't it? Yeah? D, E, G, H. Yeah? That's what it is. Okay? So that's your... and like I say, this... You must say, well, there's a plus sign here, and it's changed to a minus. And that is no mistake. Okay? That's no mistake. Okay? There's not... because that is the position or the address of the second entry, and it's got a negative in there. Clearly. One great advantage of what do you call it, of the determinant is some mathematics is too rigid. It's too, they're not for negotiation. There's no room for maneuver. That's one complaint about mathematics, which is fair enough. Some students like that kind of stuff. They like this unique answers. It's not debatable. This is it. There's no question. Okay. But one thing good about determinant is that you don't have to expand along the first row. You've got a lot of flexibility. You can actually expand along the second row if you want. You can actually expand along the bottom row, the third row. And you might say, well, why do I want to? We'll do an example where it's a great advantage of expanding along a particular row rather than just the first one. Okay? You can cut down your arithmetic quite a lot if you expand along a particular row rather than just the first one which comes up. So that's expanding along the first row. So what do you think the formula, if you expand along the middle row, what do you think the formula is going to be? If you expand along the middle row there. Come on, that's the formula for expanding along the first row. What do you think the formula for expanding on the middle row? That row there, what do you think it's going to be? What's your prediction? Go on then, Patrick.
Well, it's going to be exactly the same, apart from you've got D, E, and F.
Yeah, D times the cofactor of D, plus E, the cofactor of E, plus F times the cofactor of F, isn't it? Okay? And what about if you want to expand along the bottom row? What's the formula for that? What's it going to be? There's someone else. Sorry? Sorry, what do you say?
The same, but with G.
Yeah, exactly. G times the cofactor of G, plus H times the cofactor of H, I times the cofactor of I. Okay, that's what it's going to be, plus. So there you are. Okay, F cofactor and D. There's even more flexibility. Guess what? Guess what else you could do to find the determinant? Let's have someone else, Patrick. Guess what other flexibility? What's the obvious thing? What do you think it might what does your intuition tell you? Instead of expanding along the rows, what could you do? Yeah, you expand along the columns. You'll get exactly the same answer. If you expand along any of the columns, okay, you also want to get you're going to work out the determinant. So if you work out the first column, what's the formula if you expand along the first column? What's the determinant of the first column? Yeah, A times cofactor of A, yeah.
Plus D cofactor of D.
That's right, yeah.
Plus G.
Yeah, plus G times the cofactor of G, yeah? Okay, that's right. So there you are. So you can expand along any row or column. Doesn't make any difference. So don't worry about the transformation. Let's just work out the determinant of A here. Don't worry about the transformation. I know we haven't done transformations. And what it is, it's going from R3 to R3. That's what it's saying. But we haven't done that chapter, so I can't. But I'll go with geometric interpretation of what we mean by the determinant. So if we work out the determinant of this matrix, how would you find the determinant of this matrix? It's a good example, because how do we find the determinant of this matrix? A 3 by 3 matrix. So how do we do it? Yep. That's what I would do. Why are you expanding along the last column? There's a 0 in there. Okay, what I would do is, instead of expanding along that row, the first one which comes into my head, okay, or the first one I see. No. Think like I say, you cut down. You work quite a lot. You learn a lot if you can expand along that column there. Much easier because there's a 0 there, isn't there? And numbers are smaller as well. You could do the middle column, but the numbers are slightly bigger. Okay, I would definitely expand along either the middle row or more likely the last column, because there's a 0. So you've got no arithmetic to do there. 0 times something is going to be 0 anyway, isn't it? Okay, so let's do this. So the determinant of A is equal to what is it? Plus or minus? You've got to remember that. Is it plus or minus? It's a plus position, yeah. Plus minus plus, yeah. So either put in, I13, which is minus 1 to the power 4, which is plus. Okay, so it's minus 2. Determinant of what? You tell me. Determinant of what? Yes, cover that up. It's minus 6. Yep. 6. 3 minus 7. Okay. And then what are the second entry? What's it going to be? Yeah, it'd be 0, wouldn't it? It doesn't matter. You can put minus 0 plus 0. It doesn't make any difference, does it? Don't worry about it, do you? Times something, we don't care what it is, do we? We know it's going to be 0. Because 0 times, 1 minus 1, 5, 3 minus 7, determinant is going to be 0 anyway. Okay? What are the last entry? Yeah, plus 1 times the determinant of what? Minus 1, yep. Sorry, you can't see. Minus 1. The good thing about this thing, I can see what you can see, what you can't. Minus 1, yep. 5 minus 6. 6, isn't it? Yeah? Okay. If you work that out, so it's minus 2. This is, what's the determinant of 2 by 2? How do you work out the determinant of 2 by 2?
42.
Yeah, 42. 6 times 7 is 42. Minus 18. Plus.
Minus 1.
So that's 6 there.
Oh, 6,
Yeah. Minus 6, yeah.
plus 30.
Yeah, plus 30, yeah. So you can work that out. If you work that out, you get minus 24. Okay, if you work that out, you get an answer of minus 24. Now, of course, you might ask, well, what does minus 24 mean? Forget the minus, but I'll tell you what minus means. Let's take the value of 24. What do you think it represents? Determinant of a 3 by 3, okay? Determinant of a 3 by 3, you get an answer of, let's not worry about the minus, ignore the minus. Let's work out the determinant of a, let's put the mod sign in, which is 24. I'll tell you what the minus means in a second. It means the same thing as 2 by 2. Like Rome just said, you flip the vectors over, that's what's happening. What do you think 24 means in this case? In the 2 by 2, what did it mean? When we worked at the determinant, we've got a determinant of 8, I think, if I remember correctly. What did the 8 mean? Sorry? Area scale factor, doesn't it? How much the area is increased by. What do you think it means here? Yes, makes sense. Makes volume, isn't it? You've got 3 dimensions, isn't it? Volume. So it increases the volume by 24 times. So if you take a unit cube, okay, if you take a unit cube, not just a cube on it, but a unit cube, a cuboid, okay, you take that and you apply that matrix, this A, which is given to us, okay, if you apply that matrix, you end up with that sort of shape here on the right hand side. And if you work out this volume of this, that is going to be 24, guaranteed. The volume of that is 24. Okay, so it's a volume scale factor now. Okay, volume scale factor is R4 hypervolume scale factor. It'll be, yeah. Okay. So that's what we mean by, this is why I put a plus sign. I took the modulus, so because volume can't be negative. Well, in mathematics, Well, anyway, it can't be negative. Let's keep it like that, shall we? What do you think the minus 24 means? We've got an answer of minus 24. Remember, look. So where is it? There's minus 24. We know what 24 means. Its demand is increased by. It could be if it was 1 over 24, it would have been decreased, clearly. What do you think the minus signifies here? Sorry? Yeah, it's opposite direction. Okay, exactly. Yeah. So one's in. If this is left-hand orientation, that's the right-hand orientation. Here you change the XY, your vector. Look, X is down there, and now it's over here. Like Arob just said earlier, just flip them over. So if you change any two vectors over, you would get. If where's that matrix gone? I'll tell you one thing. If I swapped around one or two of those matrices, if this was my first column, that was my second column, then the determinant of that matrix will be 24, plus 24. Okay, if you change them around, that's what you find. Okay, same idea as what we did for 2D. All right, let's write down. That was formula for a 3 by 3, but we might have a 4 by 4 or 5 by 5. What's the formula for the determinant of a 5 by 5 or a 6 by 6 or a 7 by 7? How am I going to write it down? Let me just take the first row rather than, and then once you've got the first row, then the others are straightforward. How do you think the formula is going to work for an n by n matrix? Any clues? Come on, what do you think the formula is for an n by n matrix? How do I write down the formula for an n by n matrix? Say it's a 3 by 3. What would the formula? Say it's A11, A2, A12, A13. What would the formula be then? Come on, how did we do it? All right, if it's ABC, that's what I had. What's the formula for ABC? A times cofactor of A plus B times cofactor of B plus C times cofactor of C. What do you think it's going to be now? Go on.
Sorry.
Okay. Anybody?
Just keep that.
Yeah, it's going to be A11 times the cofactor of A11, okay, plus A12 times the cofactor of A12, plus A13 times the cofactor of A13, and so on, okay, all the way to n 1n. Yeah, okay. So your formula is given by that. A11, C11, C represents the cofactors. A12, C12, all the way to A1n, C1n. Okay, those are your cofactors. And there's the general formula. But you could expand along any row. So if you expand along the ith row, it's given by that. If you expand along the ith row, you're given by that thing there. Okay, what we do is I need to find what we mean by the cofactor matrix. The cofactor matrix is the capital A represents the cofactor of A, capital B represents the cofactor of B, capital C represents the cofactor of small c, and so on. Okay, well, I want to find the cofactor. This is going to help me. I know you can think, well, where's it going? They've helped me to find the inverse. I want to find the inverse. I want to get to the inverse of a 3 by 3. That's why I need all this. Now, let's find the cofactor. I want to just find some of the entries. Let's find the cofactor matrix C of this 3 by 3 matrix. Let's just do 1 or 2 entries. How do we find the cofactor of 1? What's that going to equal? What's the cofactor of 1? What's the cofactor of 1? Come on, we don't cofactors. How do we find the cofactor of 1? Well, I don't want the answer. Tell me how you do it. I'm not worried about that. Yeah, 1 times. Sorry? The determinant, yes. 9, 7, 1, 0, isn't it? Yeah? Which is equal to 9 times 0, yeah? 9 times 0 minus 7, isn't it? Yeah? Okay. Okay, what about the cofactor? So that's minus 7. What are the cofactor of minus 1? This is the cofactor. I don't want the number in front. I just want the cofactor.
3, 7.
Well, it's a minus, isn't it? Yeah, it's a minus sign. Yeah, it's plus minus. Yeah, so minus determinant of what? Go ahead.
3, 7.
Yeah, 3, 7
Minus 2, 0.
minus 2, 0. Okay, which is minus 0 plus 14, isn't it? Yeah. So it's minus 14, isn't it? Yeah. Okay, it's minus 14. So you can go through the whole process, and you'll find that the cofactor matrix. You work through all this, you find the cofactor matrix is given by this thing here. So if we found the first two, yeah, minus 7, minus 14. You can find the rest of the entries in the same way, okay, and you find that's a cofactor matrix. And what you really want to, in order to find the inverse, is to find the adjoint of this matrix. The adjoint is simple. The cofactor matrix is a bit tedious, okay? The adjoint is just the transpose of that matrix. If we transpose that matrix, what do we get? The adjoint of A is equal to CT. If we transpose that, what do we get? If we transpose minus 7, minus 14, 21, yeah, 5, 10, 1, minus 52, 8, 12. If we transpose that, what do we get?
Minus 7, 5.
Yes, right, yeah, either minus 7, minus 14, 21 goes down there, doesn't it? Yeah, okay. And you said, go ahead.
5.
5, 10, and 1, yeah? And the last column is what?
Minus 52.
Minus 52, 8, and 12. Okay, we need the adjoint. So the adjoint of that is given by this. Okay, well, what do we need all these? I find quite a lot of terms there: cofactors, adjoint, minor, and so on. Okay, it's all to do with the inverse of a matrix. The inverse of a matrix. The inverse, okay, of a matrix is what we need. Now, what I do want, I need this result. This is the result. I'm not going to prove this result, but I do need this result for to do the second proposition. This is like a lemma. This is. I want to show the second proposition. So, I don't know if you want to copy this down or you've got it in your notes. You've got it in your notes, fine. What it says is if you multiply the entry of the cofactor plus entry of the cofactor plus entry of the cofactor. Okay, if you add them all up, you get determinant of A when I is equal to J and 0 everywhere else. Okay, 0 everywhere else. We'll see what it looks like in a second. So I don't want to spoil your show. I don't want to show you what it looks like at the moment. Now, what I want to get to, using that, I want to get down to here. I want to show this. A times the adjoint of A gives you the determinant of A times I. So how do we prove this? Let's prove this one. How do we prove this? Well, if we look at one piece, if we look at A, the matrix which is given to us, the adjoint is a cofactor matrix, isn't it? Okay, transpose. So if we look at this, if we multiply the left-hand side, let's just take one entry. Let's not worry about all the entries. Let's just take one entry, okay? If you multiply one entry, that row by that column, okay, remember matrix multiplication. So if you work out, A times the adjoint of A for entry IJ, let's say, or I, whatever it is, okay, what do we get? How do you multiply a matrix by another matrix? What do we get? I know it's hard, this is abstract, that's why maybe it's hard, but you don't want to pay this university a lot of money to have an easy life. Just do the one I highlighted, just do that entry. I'm not worried about this. Once you do one entry, then the others are going to be easy. Go on then.
Would that be AI times C, like
yeah, so can't you move, you can't see. Yeah, AI1 times C, whoops, out of focus, isn't it? CJ1, yeah? Okay, CJ1. AI2 times CJ2 all the way to AIN times CJN, isn't it?
Yeah.
Okay, so that is going to be AI1 times CJ1, okay, plus AI2 times CJ2 plus all the way to AIN CJN. That's what it's going to equal. Okay, if you do that. Now, if you use the, like I said, I wanted to use that previous proposition. If you use the previous proposition, that said this thing here, that said that if you do sum those, okay, this is what you get. So what does that look like? What's that going to look like? So what do you think A times add A, the whole lot now, what's that going to look like, the whole lot? What does it look like? Not just that entry. That entry says it's determinant of A if I is equal to J and 0 elsewhere. So if I multiply the whole lot out, what am I going to get? What sort of matrix am I going to get if I use that? What do you think this matrix is going to look like? Come on. What's the first entry? What's the first entry going to be? The 1, 1 entry. Go on.
It'd be A1 plus.
No. What would it be? No. You use that. Use what's up there. Use this proposition. Yep. Determinant of A, isn't it? Okay. This is A1, 1, isn't it? When I is equal to J, yeah? So this will be determinant of A, yeah? What will be the second entry? We've got n by n matrix, okay? We've got a square matrix, find the inverse. What a second entry? What's that going to be? 0. Yeah, it's going to be 0, isn't it? I is not equal to J, yeah? That's equal to I1, 2, isn't it? That address there is 1, 2, isn't it? First row, second column. So I is 1 and J is 2. 1 doesn't equal 2, so that's going to be 0. Second or the third entry here. Yeah, 0 all the way. They're all going to be 0, aren't they? Because so where do we have non-zero entries in the whole matrix? Where are you going to get non-zero entries? Sorry? Yeah, along the leading diagonal, isn't it? That's where it's going to be. It's going to be, so you're going to get det A, okay, what you're going to end up with, det A, okay, all the way, det A there, zeros and zeros, aren't you? Everywhere else is going to be zeros, because I doesn't equal J. The only time where I is equal to J is along the leading diagonal. You know, A11, A22, A33, A44, A55, all the way to ANN, which may be A10,000, 10,000, whatever. Okay? Everywhere else is going to be zero. That's what this says. Look, that's what that says, isn't it? Yeah. When I is equal to J, you get det A. Okay? I is not equal to J, you get 0. So, what can you do with this? Det A out, can't you? Yeah, you can take the determinant out, can't you? Yeah? You can say this is equal to det A, and what do we have inside? The identity matrix, don't you? You get 1, 1, 1, 1, and zeros everywhere else, which of course is det A times the identity matrix. So get that. So you were asked to show, where's that proposition? You were asked to show that if you multiply that A times adjoint A, you get det AI. That's what we've got. Look, A times adjoint A, okay, is equal to det AI. So A times adjoint A is equal to det A times I. All right. So what I would do, if you've got, if you do n by n, just do one entry. That's what we're going to do. I just did it for one entry, IJ, whatever it was, and then I looked at that one, and then I used the previous proposition. Otherwise, it's a very difficult proof if you try to do it for every single entry. Okay. So, all right. Let's prove this. Let's prove this then. How do we prove this? The det A is not 0, then the determinant, then the inverse is given by this. How do I work this up? How do I show this then? Okay, I'll give you a clue. The one we've just shown, we've shown that A times the adjoint of A is equal to det A I. Yeah? And we want to show that. How do we prove that then? How do we prove this? Yep.
What you could do is you could put the A onto the other side to make it the
Which A?
the
No, I wouldn't do that. No, not A.
inverse of the A.
No, I wouldn't do that. No. So you see, I divide. Determinant is not. We're sorry, it's not zero. So you can divide by the determinant, can't you? Yeah? You've got this result, yeah? Okay. So we are given. We have from previous proposition. A times the adjoint of A is equal to det A I. Okay, so like you say, you're told that det A is non-zero. Okay, so you can divide by the determinant, so you get 1 over the determinant of A times adjoint A is equal to I. But I want to show this. How do I show that? Let me zoom out this. How do I show that top result there? Should be obvious now, shouldn't it? Yep. Yeah, because that's scalar. Yeah, A times 1 over the det of A and the adjoint of A is equal to I. Yep. So, sorry. This must be A minus 1. It's got to be the inverse. A times something is giving you I, hasn't it? Yeah. A times B has given you I, so B must be the inverse. Yeah. This has got to be the inverse. This can't be anything else. Okay, because that times that gives you I. Okay, so A minus 1. A minus 1 is equal to 1 over det A and the adjoint of A.
I see.
Okay, there's your result. There you've shown it. Okay, let's use. I mean, determinants aren't easy to do. They're a bit laborious to work out. I mean, you know, we want to find the inverse. Inverse of a matrix is one of those tedious tasks we've got to do. Like I say, I try to avoid as much as I can. If you can avoid it, like that's why we discussed orthogonal matrices last week. Okay, sometimes you can't. And you know, if you want to find the inverse, if you say, for example, if you've got a 10 by 10 matrix, okay, 10 by 10 matrix, then you know you've got to make nearly 3.5 million calculations, 3.5 million operations. Okay, take quite a lot of computing time. So determinants aren't very. This is why I always leave this. I know in further maths they do this quite early. Some people say, "Why did you do this earlier on?" It can make life easier some ways for to find whether the set of vectors are linearly independent, but they're not very intuitive. And calculations, like I say, are a bit tedious. Like I say, if you've got a 10 by 10 matrix, you know you've got 3.5 million operations, computing operations to do. Okay, you've got 100 elements in there. Got to find all the determinants of all the cofactors and everything else. You know, that's why I try to avoid. We all try to avoid as much as we can. Like there was an American guy, Dan Axler, who said he wrote an article called "Down with Determinants." We should do everything without determinants. I found that I could do everything without determinants up until one of the next chapter 7, when I need eigenvalues, eigenvectors. That's another way around it, which is transformations, I suppose. But anyway, let's find the inverse of the matrix that was given to us in example 8, which was this. How do we find the inverse of this matrix? We've done all the hard work. We've definitely done all the hard work. How do you find the determinant of this? Well, yeah, that is to find the. Oh, sorry, determinant. I mean, find the inverse. To find the determinant, you're right. To find the. How do you find the inverse of this? We've done all the hard work. I mean, the inverse is given. Clearly, the inverse is given by that, isn't it? Yeah. Sorry. The inverse is given by that thing there, isn't it? Yeah. What's the adjoint of A? What's the adjoint of A? We worked that out earlier. Okay, the adjoint of A, if you work it out, was the cofactors transposed. That's what it was. Okay, that was the adjoint of A. What else do we need to find? What else do we need to find? Look, A minus 1, there it is. A minus 1 is given by that. So we found this bit. There it is. For for the given matrix. There it is. Okay. So what else do we need to find? Yep.
You need to find the determinant
Yeah.
of A.
We need to find the determinant of A, and like the fig said, determinant of A, I'll expand along the bottom row. Yeah. So determinant of 1 minus 1 5 3 9 7 minus 2 1 0. And I quite agree. I would explore. What did I put down? What did I, oh no, that's right. Minus 2 1 0. I'm trying to find the inverse of that one. I thought we were all down wrong. Okay, you've got to find the inverse of not the transpose matrix, or not the cofactor, but the original matrix. Okay. So how do we find? And I would expand along the bottom row. Totally agree with that. Okay. Plus minus plus. So you tell me. I want to expand along that row there. Come on. Yeah, minus 2. And what's the determinant of the remaining piece?
1, 5.
Yeah, cover that up. Minus 1. Determinant of minus 1, 5. Yep. 9, 7. Yep. Yeah, minus 1. Plus, minus, plus, minus. Yeah, minus 1. Yep, go ahead. Determinant of what?
1, 5.
1, 5. Yeah.
3, 7.
3, 7. Yeah. 1, 5, 3, 7. And what else have we got? Plus 0, isn't it? We don't work it out, do we? We don't work that out. But, you know, sure, you don't want to spend your time doing that. Minus 2 times what? Yeah, minus 7. Minus 45. Minus 7 minus 15. Okay. You work all this out. You get to a value of 112. Well, I assume all the minuses cancel each other out or something. Okay, you've got a value of 112. Okay, so the inverse, A minus 1. Okay, A minus 1 is what? What's it going to be? What's going to be the inverse of the matrix? What's the first? What do you write down? Yeah, 1 over 112, isn't it? 1 over 112. So there it is, 100, and the cofactor matrix transposed. There it is, okay? 112. If you asked to find the inverse, I wouldn't do that first. I think I sort of highlighted this earlier on, okay? I wouldn't do this first. The way I done it there, I wouldn't do that. The only reason I did it that way is because I already had the cofactor matrix. That's why I did it. No other reason. Because the matrix which we had done in the earlier examples. So what would you do first? Find the inverse. I know you understand. Let's have someone else. What would you find first? Yeah, the determinant, wouldn't you? Find the determinant, yeah? The first thing you want to do is find the determinant. You don't want to waste your time finding the cofactor matrix. 2 by 2 is not too difficult, okay? But for a 3 by 3, do not go around finding all the cofactor matrices and find the end. Oh, there's no inverse. So what you first want to do is find the determinant. And this determinant is okay, 112, none 0. So I had an inverse. If the determinant was 0, what could you say?
No.
Yeah, it's got no inverse. Okay. Any questions on that? Any questions? Okay, I want to start section C. Can I use your book for a second? So I don't bring my notes with me. Section C.